Hey, hello. So let's look at containerizing a TensorFlow classification task. All right, we want to go through and classify all of our audio and to see what comes out. What's the quickest way that we can run this against all of our audio data? And the answer is to containerize it and run it as a Kubernetes job. This makes it scalable, and this makes it as fast as possible to run in a parallel process. If you try to just do it in a Jupyter notebook or even as a standalone script, TensorFlow won't always work nicely with parallel processing from like the multiprocessing pool. It ends up making that parallel job into a series. So they just don't run one after the other. At least whenever I've ran it before. Might end up being different, but TensorFlow previously has always seemed to be very greedy with the CPU. So one instance of it and calling the model to predict takes up all available resources on that CPU to do it. And so any other times that we're calling it, it gets stuck behind it. So it ruins our parallel processing. The way to fix that is to create this into a container environment. So that way all of your resources are isolated. And then you got to run that container environment. You could always do it, from the command line, just, do a for loop and run that container as multiple times. What we're going to do is we're going to put it on Kubernetes as a job. So that way that can control the processing of all these jobs with the advantage of that being scalable. So if we needed to instead of classifying 105 birds with like 50 audio files each, if we wanted to classify, 4,000 types of birds with thousands of audio files each, we can scale this up to multiple nodes at once, multiple actual machines running it, all with this one container. So let's look at how we do that. It's really not too difficult. We just have this one Python script that has really similar imports to before, except this time we're adding redis because that's going to be kind of our job management system. It's a very reliable way for all the other tasks to kind of check what process they should be running on and a place that they can put all their results. So yeah, that's why we have Redis here. Google Cloud Storage because we're pulling in all that audio data from there. Again, really similar to before, 16K audio, 1024 for our W value for NFFT. Spectrograms, again, 512 by 512 because that's what the model was trained on. And we're changing our skip value here to 512. So we're only going to classify each portion of audio once. We're not going to overlap anything. I'm actually having to go back and rerun this because originally I had overlapped it. And I didn't realize until the middle of the video that shouldn't have done that. And the reason why is because going back and checking through the scores, it doesn't make everything line up properly. I want individual discrete windows with one classification each. So we're making a Redis connection here, grabbing in that same Florida Bird JSON file. So we have all the information of what assets should be running with it. Same downloaded wave, same create spectrogram. So we're just making our mono 16K wave file. We added this to where we're actually going to delete that file when we're done with it because we don't need it anymore. And we don't, since this is running in a pod, we don't want that pod to fill up. So we're just going to remove and clean up the data as we're moving. Create spectrogram is the exact same as before, just sliding over the audio, calling fast Fourier transform every W units. Okay, so here's where we're loading up the model that we trained. And then here's our getBird function, which is, again, pretty similar as before. Grabbing that bird information, grabbing all the audio files for it, and then we're enumerating over those audio files up to some max files amount. First, we were checking to see, all right, so all of this data is going to be stored in Redis, all of our output from the model, the classifications. So the first thing that we're going to do is check and see if that's already been classified. That's because I've ran this multiple times before. So like if it ran and then we came across an error, but we already came up with classifications, we don't want to reclassify those. So first things first, we check and see if we've already done this work. If we do, move on to the next. If not, then we try to download our audio file, convert it to float32 audio, create a spectrogram from it, then come over here and enumerate through it. Again, the exact same way we did with our training data. And we're going by skip amount though, that's the same size as our width. We're making sure that we at least have one spectrogram, and as long as we at least have one, then we are calling model.predict on those spectrograms. Right, we're wrapping it as an NP array because it likes it, and then we're calling model predict on all of them at once and getting all those classifications back out. And then, so when they come back out, they are coming out as a list. Let's see. Let's say we send in 10 spectrograms. It'll come out as a 10 item long, 105 wide array, right? Because of it's 105 classes. So each class is going to have some value, right? We're using kind of softmax on it to, you know what, whenever we train this, I don't think I ever added softmax to it. I might have. It should have softmax anyway. So one of those values is going to be higher than all the others, and that's going to be the class that we say was predicted for that instance. So because of that, we're calling np argmax on it, and we're setting the axis to 1 because we're looking at from the width, right? Which one over the width is the largest value, and the index of that largest value is what our value is going to be here. So index 4 is 0.9, everything else is like 0.0 something, whatever. Then that's the index it's going to win, and that's going to be our index out. Then we're converting it to a string, converting it to a list, and we're joining it by a comma, so that way we can write it to this value here, because it expects a string, so we give it a string. Then we are making sure that we remove that wave file and continuing on. So this is the whole script. Well, I guess the initialization of it, right? It sleeps for some random number of time. It grabs, so in Redis we have a list called class indexes, and it's pretty much just a list of numbers 0 through 104. And whenever this starts up, it pops a number off that list, and that's the class that it works on. So we know that because it's Redis, it's ready for everything to ask it everything at once, and it's going to handle all of that traffic in a sane fashion. So we know that it's only going to spit out one class index, and that's what's going to run here, and that's what we run. So that's the Python script side of it. Here's our model, FloridaBirds.h5. Here's our bird data, FloridaBirds.json. And here's our new UKey fast Fourier transform library. Thank you. And let's see. All right, so other interesting things here. Let's start with the Docker file. Docker file is just Python 3.6. We install the libraries that we need: TensorFlow, NumPy, Google Cloud Storage, Redis. Install ffmpeg. We make some directories and own them by user 1000. This isn't important on the Kubernetes side of things, but when I was running this locally, it's really nice. So that way, if you have like the volumes mounted and some data is being written, it's written as the user ID 1000, so it usually matches your main user. Copying our source over, setting that as a work dir, and then running it. We add this -u flag so that way it makes sure that it actually streams the output to the logs. All right, boom. Simple, easy Docker file. From there, let's look at Redis real quick. This Redis file has two things in it. It's our service and the deployment. On Kubernetes, the deployment handles to make sure a pod is running. A pod is just pretty much a container. And to be fair, a deployment could be a group of containers. In this case, it is one container, just one Redis container. And that's what it knows under the spec here, replicas 1. So this deployment will ensure that there is one pod running that matches this spec here, which is running image Redis 6.2.0 and some container port. And then the service here gives everything else access to that. So the service has a selector, app Redis, which matches this information down here. It knows the way to share this port, and so it opens it up so that way other services can access it. So running this file right here, of 34 lines, Kubernetes will automatically grab Redis, start it up, give everything else access to it when it wants. Okay, so here's our job. Now the job is 15 lines, and it's the spec right here that says to create this container that we've called Classy. Never restart it, never repull it. That's because it's a local image. Really, if this was something that we had on the cloud, like we use a container registry for it, we would change these values. But in this case, we're running it locally, so it's actually pulling from Docker. So yeah, that's the values there. These are the important parts that we would change on a larger deployment. We have the completions value, completions of 105, because we have 105 different tasks to be running, so we expect 105 of them to run well. Our parallelism we're setting to 62 because we're running this on a 64 core box. So I just gave 2 cores for freedom. I don't know. I could probably run it at 64 and it would be fine. Maybe even a little bit more, because you don't have to really separate them per core, right? But if we were running this on a 100 node cluster, we could set the parallelism up a lot larger. So that's the job. You submit that to your Kubernetes deployment, and it's going to run this task. So yeah, that's what we were doing with minikube on the server. So let's see if we can make that happen here. Let's see if we can. Okay, we're going to go and start minikube here. We have to specify the number of CPUs and the amount of memory that it can have when it starts. Otherwise, it starts at some really low value. So we set the memory. We're going to set that here to equal to 200. And CPUs equal to 64. And we say start. And it's mad because I don't have Docker running. Okay. So it's creating that container with 64 cores and 200 gigs of memory that we then can run, treat it like a Kubernetes cluster, and run this job on. This is the job spec that we will be running. Yeah, nice and easy. Just going to take up 62 processes at once, and we're going to expect 105 completions from it. Here's our classifier. Again, we've set the skip to 512 this time. So everything should be good. So let's start with a few simple things. kubectl get nodes, not nodes, nodes. There we go. So there's our main minikube node. We can get pods, and we can see that we have all of our previous pods running, and Redis is still running. Wow, I didn't think that they would still be going. Well, let's go ahead and clear those out. kubectl delete job classy, and for Redis we'll just redeploy that. So kubectl apply -f our Redis file, and nothing changes. So Redis is still there and fine. Let's see. Actually, you know what? For clean sake, let's just go and delete it. kubectl delete deployment Redis, and also the service. And then we'll redeploy it. Now we have Redis. And there's this nifty command, yeah. Minikube service -- URL Redis will give us a URL into Redis. Now what are we going to do with that? We're going to go into Python, and we're going to import Redis. And we're going to say r equals redis.redis at that server, which was what? 192.168.49.2. And the port is equal to 3131214. And if we say, let's see, r dot, the length of this list class indexes should be 0 or non-existent. Okay. And I think if I do for I in range 105, because that's the number of classes that we have, r dot l push class indexes and then I. So that's really all we need to do here, was go into Redis and make this this list of class indexes from 1 through 104. So we come over to here, and we want to run that job now. Well, here, actually we need to do 2 things first. We need to connect minikube to the Docker environment. That's this command here. It's eval minikube Docker environment. That allows us to build a container like this, Docker build, and tag it classy, this local environment right here. So we built our container, pretty much all from cache anyway. And then we're going to start it. That command right here, eval minikube docker environment, allows us to build that Docker container locally, and then minikube will look there for that image. Without this, you kind of need to use a container registry, which is where you'd eventually go to for production anyway, but yeah, this works. Kubectl apply -f job.yaml. And then let's check on that job. Kubectl describe job classy. And classy looks to be going all right. Let's see, we have 62 pods running. 0 have succeeded and 0 have failed. So let's see what the output of those pods look like. Kubectl logs. So it's going, right? You have our TensorFlow import output. This pod right here is looking on the black-throated blue warbler, class index 86. It's working on asset index 0, which is asset ID 61074531. And if we run that output again, it's still doing the same thing, right? Okay, then we ran it again, and it's moved on to the next, right? Moving on to asset 1, and this other asset E. So, Python 3, import redis. Needing to copy that command right there because of, yeah, if you connect to it with strict redis, then it automatically will parse all this stuff out for you, and it's a lot nicer. Strict redis port. I guess the DB is going to default to 0 probably. Have we just say decode responses equals true. And r dot h get all asset class. Assets class. There it is. Okay. So here's all the data that's being populated by these running tasks. Right? We can find that we have a, there we go, an asset ID, and then a comma separated value of the classes coming out of it. I guess in this case it's just 93. But here's one that it's picked 44 every time. Right, here's one that picked 59, 22, 42. This one, it's pretty determined that it is class 97. So what are we going to do with this? We're going to import JSON. Maybe. And we're going to say, let's see, JSON.dump r.hgetall asset class. And we're going to dump that to, I just call it scores.1.json. Oh, gotta open that file. Open scores.1.json for writing and dump it there. Okay. And then just for sanity's sake, we can always read that back in. JSON.load open scores.1.json. And the length of those scores, 545. That looks like that, right? So we're having to write it to JSON ourselves manually because Redis is an in-memory database, right? Like if it craps out, it's going to lose all this information. So if any reason this job stops in the middle, I don't want it to lose this information. So I'm just manually saving it every now and then. We could configure Redis to do this automatically. Again, if this was a larger production deployment and we were running this job task for, like, let's say a week, we definitely want that to automatically happen. And you could configure it to be so. But for right now, this thing takes like, I don't know, I think it's like an hour or so to run. Look at that. Look at all those instances running. Look at that nice 64 cores all being used up. In this case, 57 on the screen, but it's a lot of processing going on. So that goes through. We create this scores.json file that we later use to filter out all of our training data to go through this exact process again with smaller window sizes. So thank you for watching. Hope you enjoyed it. Kubernetes is awesome. The job spec on Kubernetes is really awesome. Like for any sort of data processing, you can parallelize that task and you can throw it on a lot of servers at once really quick. So yeah, enjoy.